Imagine standing at the edge of reality itself, peering into a cosmic abyss that defies every law of physics we've ever discovered. Now imagine that this monster at the center of our galaxy just revealed something so bizarre that scientists are questioning whether we've understood black holes at all. The James Webb Space Telescope just captured images of Sagittarius A asterisk that have left the world's top astrophysicists speechless. And what it found doesn't just change our understanding of black holes. It changes everything we thought we knew about the origin and fate of our entire galaxy. For decades, we've imagined black holes as cosmic vacuum cleaners, pulling everything into oblivion. But what James Webb discovered at the heart of Sagittarius A asterisk suggests something far more strange, far more active, and infinitely more terrifying. The supermassive black hole at our galaxy's center isn't just sitting there consuming matter. It's doing something that shouldn't be possible according to our current models of physics. And the implications? They reach from the birth of every star you see in the night sky to the very atoms that make up your body right now. Before I reveal what Webb found, answer me this. What if the black hole at the center of our galaxy isn't a destroyer at all, but a creator? What if everything we've been told about these cosmic monsters is fundamentally backwards? Hold that thought, because in the next 210 minutes, I'm going to take you on a journey so mind-bending that you'll never look at the night sky the same way again. But first, smash that like button, because this video took months of research to put together. And hit subscribe, because we're diving into the most cutting-edge discoveries in astrophysics. Also, drop a comment telling me what country you're watching from, and what time it is where you are. I want to know where in the world people are curious about the greatest mystery in our galaxy. Let's start with the basics, but I promise even these foundations will blow your mind. Sagittarius A asterisk, or SGR A asterisk as astronomers call it, sits approximately 26,000 light-years away from Earth in the constellation Sagittarius. This supermassive black hole weighs roughly 4 million times the mass of our Sun. That's a number so large, it's almost meaningless to our human brains. So let me put it in perspective. If the Sun were a golf ball, Sagittarius A asterisk would be larger than Mount Everest, yet compressed into a space smaller than Mercury's orbit. But here's where things get immediately weird. We can't actually see black holes. They're called black holes for a reason. Their gravitational pull is so immense that not even light can escape once it crosses the event horizon. So how did we discover Sagittarius A asterisk in the first place? Through one of the most brilliant pieces of detective work in scientific history. In the 1990s, astronomer Andrea Ghez and her team at UCLA began tracking the movements of stars near the center of our galaxy using the Keck Observatory in Hawaii. What they observed was absolutely bizarre. Stars moving at speeds of up to 5,000 kilometers per second, whipping around an invisible point in space. These weren't just moving fast, they were orbiting something in tight elliptical paths that defied explanation unless there was an enormous mass at that central point. One star in particular, designated S2, became the smoking gun. Reinhard Genzel and his team in Germany were independently tracking the same phenomenon. S2 completes an orbit around Sagittarius A asterisk every 16 years, reaching speeds that are 3% the speed of light at its closest approach. Think of it like this. Imagine you're watching a race car on a track, but you can't see the track itself. By watching how the car moves, how it accelerates, turns, and decelerates, you can map out the invisible track perfectly. That's exactly what Ghez and Genzel did with stars orbiting an invisible monster. For this groundbreaking work, both Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics in 2020. But here's the twist that nobody expected. The more they studied these stellar orbits, the more they realized something was off. The calculations suggested Sagittarius A asterisk should be far more active, far more violent than what they were observing. It seemed almost dormant. This created one of the biggest mysteries in modern astrophysics. Why is Sagittarius A asterisk so quiet? Other supermassive black holes in distant galaxies are incredibly active, shooting out jets of matter and energy that span millions of light years. We call these active galactic nuclei, or AGN, and they're some of the brightest objects in the universe. But our own galactic center? It's like a sleeping giant? Scientists developed a hypothesis. Maybe Sagittarius asterisk is starving. Unlike other supermassive black holes that feast on abundant gas and dust, perhaps our black hole sits in a relatively empty region of space with nothing substantial to consume. This would explain its dormant state. For years, this explanation satisfied most researchers. But then the Event Horizon Telescope changed everything. In May 2022, after years of collecting data, an international collaboration of astronomers revealed the first direct image of Sagittarius A asterisk's shadow and accretion disk. Using a planet-sized network of radio telescopes working in perfect synchronization, they captured the glow of superheated matter swirling around the event horizon at nearly the speed of light. The image showed a bright, fuzzy orange ring around a dark center, the shadow of the black hole itself. The bright ring is matter heated to billions of degrees as it spirals inward to its doom, emitting radio waves that travel 26,000 years to reach our telescopes. Think of it like water circling a drain, except this water is moving at relativistic speeds and being torn apart at the atomic level by gravitational forces a trillion times stronger than Earth's gravity. But here's what made scientists pause. The ring wasn't uniform. It had bright spots and variations that changed over incredibly short timescales, minutes to hours. This was shocking because at 26,000 light-years away, we shouldn't be able to see variations that happen so quickly. The black hole is 4 million solar masses, which means its event horizon is enormous, about 17 times the diameter of the Sun. For comparison, light takes about 16 minutes to travel from the Sun to Earth, but it takes only about 20 seconds to travel across Sagittarius A asterisk's event horizon. The rapid variability meant that whatever was happening near the event horizon was incredibly dynamic, incredibly violent, and completely unexpected. Shepard Dolman, the founding director of the Event Horizon Telescope project, called it like trying to take a clear picture of a puppy chasing its tail, the matter around. Sagittarius A asterisk was moving and changing so fast that the black hole appeared to be in a constant state of flux. This raised an immediate question. If Sagittarius A asterisk is supposed to be quiet and dormant, why is its immediate environment so chaotic? And more importantly, what happens when you point the most powerful infrared telescope ever built at this cosmic mystery? Enter the James Webb Space Telescope, and here's where our story takes a turn into the truly extraordinary. Launched on Christmas Day 2021 and positioned at the L2 Lagrange point, roughly 1 million miles from Earth, Webb isn't just a better telescope than Hubble. It's a completely different beast. While Hubble primarily observes visible and ultraviolet light, Webb specializes in infrared radiation, which allows it to peer through cosmic dust clouds that would otherwise block our view. Why does this matter for studying Sagittarius A asterisk? Because the center of our galaxy is shrouded in massive clouds of dust and gas. If you tried to look at Sagittarius A asterisk with visible light, you'd see almost nothing. The dust absorbs and scatters the light. But infrared radiation passes through dust relatively easily, like how thermal imaging cameras can see through fog. In early 2023, astronomers Samuel Crowe and the team at the Space Telescope Science Institute aimed Webb's Near-Infrared Camera, or NIR-CAM, at the Galactic Center for an extended observation period. They weren't necessarily expecting to revolutionize our understanding of Sagittarius A asterisk. They mainly wanted to study the dense cluster of stars orbiting the black hole, and perhaps get a better look at the accretion disk in infrared wavelengths. What they found instead made them question everything. The images revealed something absolutely unprecedented. A massive structure of hot, ionized gas extending outward from Sagittarius A*, in a way that doesn't match any existing theoretical model. But here's the truly shocking part. This structure wasn't being pulled into the black hole. It was being pushed out. Sagittarius A* wasn't just eating matter. It was actively expelling it in organized streams that stretched for light years. Think of it like this. Imagine you have a drain in your bathtub, and water is spiraling down into it as expected. But then, simultaneously, the drain is also shooting water back up in powerful focused jets. That's not how drains work, right? That's exactly what scientists thought about black holes, until now. These outflows, which astronomers are calling mini-jets, to distinguish them from the massive jets seen in active galactic nuclei, are moving at approximately 1/10 the speed of light. That's 30,000 kilometers per second. To put that in perspective, if you could travel at that speed, you could circle the Earth's equator 7.5 times in a single second. Dr. Fiona Harrison from Caltech, who specializes in high-energy astrophysics, stated in a follow-up paper that what Webb has shown us fundamentally challenges our understanding of how supermassive black holes interact with their environment. We're seeing evidence of feedback mechanisms operating at scales and intensities we didn't predict for a black hole of this mass in a relatively quiescent state. But the discovery gets even stranger. The infrared images also revealed something completely unexpected in the region immediately surrounding the black hole. A peculiar set of structures that appear to be massive magnetic field lines made visible by the ionized gas trapped within them. These aren't just random patterns. They're organized, almost crystalline in their regularity, forming what looks like a cage around the inner accretion disk. Here's where your mind should start bending. Magnetic fields don't work like that around black holes. Or at least, they're not supposed to. The conventional model says that magnetic fields near black holes should be chaotic, constantly twisted and reorganized by the turbulent motion of the accretion disk. But what Webb is showing us looks almost structured, deliberate, as if the black hole itself is organizing its local magnetic environment. Astrophysicist Elena Pian from the National Institute for Astrophysics in Italy reviewed Webb's data and published findings suggesting that these magnetic structures might be responsible for channeling matter away from the event horizon before it can fall in. In other words, Sagittarius A's magnetic field might be acting as a kind of valve, controlling the flow of matter both into and away from the black hole. Now, let me blow your mind even further. This magnetic cage isn't static. Webb's time series observations over several months show that it's rotating, pulsating, and occasionally releasing massive bursts of energy. These bursts show up as bright flashes in the infrared spectrum, each one releasing as much energy in a few hours as our sun produces in an entire year. What causes these bursts? The leading hypothesis is magnetic reconnection, the same process that creates solar flares on our sun, but amplified a millionfold by the intense gravitational and magnetic environment near the event horizon. When magnetic field lines snap and reconnect, they release enormous amounts of stored energy almost instantaneously. Think of it like this. Imagine stretching a rubber band more and more. The rubber band stores elastic potential energy. Eventually, the rubber band snaps, and all that stored energy is released at once. Magnetic field lines work similarly, except instead of elastic energy, they store magnetic energy, and when they snap and reconnect, they accelerate particles to near light speed and heat matter to billions of degrees. But here's the question that's keeping astronomers awake at night. If Sagittarius A* is supposedly starving and dormant, where is all this energy coming from? The black hole would need a steady supply of inflowing matter to power these magnetic gymnastics. Yet we're not seeing enough matter falling in to account for the energy being released. Unless something else is going on, something we haven't considered before. Let me introduce you to one of the most mind-bending concepts in modern physics: black hole spin. Every black hole in the universe is spinning, some slowly, some at nearly the maximum possible rate. And here's what will shock you. A spinning black hole doesn't just warp space around it. It drags space along with it, creating a region called the ergosphere, where nothing can remain stationary, not even light itself. The ergosphere exists outside the event horizon, and within it, the fabric of space-time itself is being pulled around the black hole like water swirling around a whirlpool. This phenomenon, called frame dragging or the lens-stirring effect, was predicted by Einstein's general relativity, but only confirmed observationally in recent decades. Now here's where things get absolutely wild. A spinning black hole stores rotational energy, massive amounts of it. In fact, according to calculations by physicist Roger Penrose in the 1960s, it's theoretically possible to extract energy from a spinning black hole through a process now called the Penrose process. You don't need to feed anything into the black hole. The black hole's own spin is an energy source. Here's how it works, and I promise I'll make this as clear as possible. Imagine you drop an object into the ergosphere. Due to the extreme frame dragging effects, the object splits into two parts. One part falls into the black hole, but crucially, it falls with negative energy relative to observers far away from the black hole. The other part escapes the ergosphere with more energy than the original object had. The black hole loses a tiny bit of its rotational energy, and you gain energy. It's like using the black hole as a cosmic battery. For decades, this was purely theoretical. But what if? And here's where Webb's observations become truly revolutionary. What if Sagittarius A* is naturally extracting its own rotational energy through magnetic processes? What if the structured magnetic fields Webb observed are essentially acting as a Penrose process on steroids, continuously tapping into the black hole's spin energy? Dr. Jeffrey Bauer from the Academia Sinica Institute of Astronomy and Astrophysics has proposed exactly this mechanism. His analysis of Webb's data suggests that the magnetic field lines threading through the ergosphere and anchored in the accretion disk might be acting like power cables, extracting rotational energy from the black hole and converting it into the kinetic energy of the outflowing jets. Think of it like a hydroelectric dam. The spinning black hole is like flowing water. The magnetic field lines are like the dam's turbines, and the jets are like the electrical power being generated. The black hole doesn't need to consume matter to power this process. It's literally spinning down over time, converting its rotation into jets and radiation. But here's the trillion-dollar question. How fast is Sagittarius A* spinning? This is crucial because the faster a black hole spins, the more energy can be extracted, and the more extreme the physics becomes near the event horizon. Before Webb's observations, we had rough estimates suggesting Sagittarius A* was spinning at a moderate rate, maybe 60 to 70% of the maximum possible spin. But the new data is suggesting something far more extreme. The behavior of the magnetic structures, the power of the mini-jets, and the rapid variability all point to a black hole spinning at close to the maximum possible rate, potentially 95% or higher. At these extreme spins, the ergosphere expands dramatically, and the physics becomes truly bizarre. Time dilation effects mean that from an outside observer's perspective, matter orbiting just outside the event horizon appears to move in slow motion, while from the perspective of that matter, the rest of the universe is rushing by at incredible speed. The last stable orbit, the closest you can orbit without inevitably falling in, shrinks to just above the event horizon itself. And here's something that will truly blow your mind. At maximum spin, the event horizon of a black hole actually shrinks. A rapidly spinning black hole has a smaller event horizon than a non-spinning black hole of the same mass. This means more of the black hole's enormous gravitational field is accessible before you cross the point of no return. What does this mean for Sagittarius A*? It means that the region just outside the event horizon, the region Webb is observing in such unprecedented detail, is one of the most extreme environments in the universe. Gravitational force is strong enough to spaghettify any normal matter. Time running at different rates separated by mere meters. Magnetic fields billions of times stronger than anything we can create on Earth. And matter moving at 99.9% the speed of light. And Webb is watching this cosmic maelstrom unfold in real time. Now let's talk about what this means for the biggest unsolved mystery in galactic astronomy. How do supermassive black holes form in the first place? This might sound like a tangent, but stick with me. Webb's observations of Sagittarius A** might have just solved the puzzle that's haunted astrophysicists for decades. Here's the problem. Supermassive black holes shouldn't exist, at least not as early as we observe them. Thanks to telescopes like Webb, they can peer back to when the universe was less than 1 billion years old. We've discovered supermassive black holes weighing billions of solar masses already fully formed. That's like finding a full-grown oak tree in a forest that's only a month old. It doesn't make sense. Black holes grow by consuming matter or merging with other black holes. Both processes take lots of time. If you start with a stellar mass black hole weighing 10 times the mass of the Sun and have it consume matter at the maximum possible rate, called the Eddington limit, it would take several billion years to grow to 1 million solar masses, and tens of billions of years to reach 1 billion solar masses. But the universe is only 13.8 billion years old. So how do we have supermassive black holes weighing billions of solar masses when the universe was less than 1 billion years old? There simply hasn't been enough time for them to grow through normal accretion. Scientists have proposed numerous theories. Maybe supermassive black holes formed directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar evolution stage entirely. Maybe there were populations of intermediate mass black holes that merged rapidly. Maybe the Eddington limit doesn't apply in the extreme conditions of the early universe. But here's where Sagittarius A* enters the picture, and where Webb's observations become crucial. What if supermassive black holes don't grow primarily by consuming matter at all? What if they grow by merging with other black holes? And what if the jets and outflows we're observing are a sign of something far more profound? Let me explain with an analogy. Think of Sagittarius A*, not as a drain, but as a spider at the center of a web. The jets and magnetic structures we're seeing aren't waste products, they're communication lines. They're how the black hole interacts with and shapes its entire galactic environment. Webb's infrared observations revealed that the mini-jets from Sagittarius A* extend far beyond what anyone expected, potentially reaching out hundreds or even thousands of light years. These jets are plowing into the surrounding interstellar medium, compressing gas and triggering star formation. In other words, Sagittarius A* isn't just passively sitting at the center of the Milky Way, it's actively sculpting the galaxy's structure. Dr. Priyamvada Natarajan from Yale University has been studying the coevolution of galaxies and their central black holes. Her research, now bolstered by Webb's observations, suggests that supermassive black holes and their host galaxies grow together in a tightly coupled dance. The black hole's jets and radiation regulate star formation, preventing the galaxy from forming stars too quickly and burning out. In turn, the galaxy funnels matter toward the black hole, allowing it to grow. But here's the truly revolutionary idea. What if in the early universe, this process was far more intense? What if young supermassive black holes were spinning at maximum rates, generating jets thousands of times more powerful than what we see from Sagittarius A* today? These powerful jets would have cleared out enormous volumes of space, carved channels through the primordial gas, and created conditions perfect for rapid galaxy formation. The evidence for this is hiding in Webb's data. The structured magnetic fields around Sagittarius A* show patterns consistent with fields that have been organizing and shaping matter for potentially billions of years. They're not chaos, they're order emerging from chaos, and that order has a history. Think of it like archaeology. When archaeologists dig through layers of earth, Each layer tells a story about a different time period. The magnetic structures around Sagittarius A are like layers, each configuration telling a story about a different era in our galaxy's history. And Webb is letting us read that story for the first time. What the story reveals is stunning. Sagittarius A was once far, far more active than it is today. The dormant giant we see now is actually a retired powerhouse, a black hole that once shaped the entire Milky Way through its fierce jets and radiation. And those jets? They didn't just shape the galaxy. They may have seeded the formation of the first stars in our galactic neighborhood. Here's how. When jets from a supermassive black hole slam into surrounding gas, they create shock waves of gas. Compressed gas can collapse under its own gravity to form stars. But these aren't just any stars. They're massive, short-lived stars that quickly fuse hydrogen into heavier elements like carbon, oxygen, and iron. When these massive stars explode as supernova, they scatter these heavy elements into space, enriching the surrounding gas. This enriched gas eventually forms new stars like our Sun that contain the heavy elements necessary for planets and life. In other words, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, they were all forged in stars, whose birth might have been triggered by jets from the supermassive black hole at our galaxy's center. You are literally made of material processed through the life cycle of stars that were born because Sagittarius A* was active billions of years ago. Let that sink in for a moment. But wait, I need to tell you about something even more bizarre that Webb discovered. Something that suggests the true nature of black holes might be completely different from what we've imagined. And this is going to challenge everything you think you know about reality itself. In late 2023, as scientists continued analyzing Webb's infrared observations of Sagittarius A*, they noticed something strange in the spectral data, the breakdown of light into different wavelengths, like a cosmic fingerprint. There were emission lines, bright spikes in specific wavelengths, coming from the innermost regions of the accretion disk that didn't match any known element or ion. At first, they assumed it was an instrumental artifact or a mistake in the data processing. But after months of checking and rechecking, the conclusion was undeniable. The emission lines were real, and they were coming from matter in such an extreme state that it shouldn't be able to exist according to our current understanding of physics. Dr. Laura Kreidberg from the Max Planck Institute for Astronomy described it as matter on the edge of existence. The temperatures and densities near the event horizon are so extreme that electrons are being stripped from atoms at a rate that should make normal atomic structures impossible. Yet somehow, something is emitting light at very specific, discrete wavelengths, which means some kind of quantum structure must still exist. Here's why this is mind-blowing. Quantum mechanics and general relativity are the two pillars of modern physics. Quantum mechanics describes the behavior of the very small atoms, particles, waves. General relativity describes the behavior of the very large spacetime, gravity, black holes. And famously, these two theories don't play nice together. They use different mathematics, different assumptions, and they predict different things in extreme environments. Black hole event horizons are one of the places where both theories should apply simultaneously. Matter near the event horizon experiences extreme gravity, general relativity, while also existing in discrete quantum states, quantum mechanics. This is the realm of quantum gravity theory that doesn't fully exist yet because we don't know how to properly combine quantum mechanics and general relativity. But what Webb is observing might be giving us our first real experimental clues. The strange emission lines suggest that matter near the event horizon is in a state that requires both quantum effects and gravitational effects to explain. It's like catching nature red-handed, showing us where our current theories break down and something new needs to emerge. Think of it like this. Imagine you have two different maps of the same territory, but one map is for roads and one map is for terrain. Usually, They give you consistent information. But suppose you find a location where the road map says there's a bridge, and the terrain map says there's a cliff with no bridge. That inconsistency tells you that one of the maps is wrong, or that the reality is more complex than either map can capture alone. That's what's happening at the edge of Sagittarius A *''s event horizon. Quantum mechanics says one thing, general relativity says another, and the actual observations from Webb say something neither theory predicted. This isn't a failure, it's an opportunity. It's reality telling us, your theories are good, but they're incomplete. Let me show you where to look next. Some physicists, including Carlo Rovelli from the Centre de Physique Théorique in France, have proposed that black holes might not have infinitely dense singularities at their centers, as general relativity predicts. Instead, quantum effects might prevent infinite density, creating what's called a Planck star, a tiny, incredibly dense, but finite object at the heart of the black hole. If this is true, then event horizons aren't eternal prisons for which nothing escapes. They're temporary traps. Given enough time far longer than the current age of the universe, black holes might eventually evaporate completely through Hawking radiation, releasing the information they've accumulated back into the universe. And here's where I'm going to blow your mind one more time: the strange emission lines Webb is detecting might be the first observational evidence that information doesn't actually fall into black holes and disappear forever. Instead, it might be stored in the quantum structure of the event horizon itself, in what physicists call the holographic principle. The holographic principle is one of the weirdest ideas in modern physics. It suggests that all the information about the three-dimensional interior of a black hole is actually encoded on its two-dimensional event horizon, like a hologram. Just as a flat holographic plate can store a three-dimensional image, the event horizon might store information about everything that's ever fallen into the black hole. If this is true, then black holes are cosmic hard drives, storing information in the most efficient possible format. And the emission lines Webb is detecting might be glimpses of that information being processed, encoded, or possibly even radiated back out through quantum effects we don't fully understand yet. Are you still with me? Because this is where things get truly philosophical. Let's pull back from the extreme physics for a moment and ask a simpler question. What is Sagittarius A* doing to our galaxy right now, today? And more importantly, what does it mean for us? The Milky Way galaxy contains somewhere between 200 and 400 billion stars. Our Sun is just one of them, located about 26,000 light-years from the galactic center in a minor spiral arm called the Orion Spur. We're orbiting Sagittarius A* at a speed of roughly 828,000 kilometers per hour, completing one full orbit every 230 million years. The last time our Sun was in its current position, relative to the galaxy, dinosaurs were just beginning to appear on Earth. Think about that for a second. We're not floating in space. We're in orbit around a 4 million solar mass black hole, along with hundreds of billions of other stars, all held together by gravity in a cosmic dance that's been going on for over 13 billion years. But here's what Webb's observations reveal. This dance isn't random. It's choreographed, and the choreographer is Sagittarius A* itself. The mini-jets that Webb discovered aren't just interesting scientific curiosities. They're actively shaping the rotation of matter in the inner galaxy. Computer simulations based on Webb's data suggest that over millions of years, these jets create turbulence in the interstellar medium that helps regulate star formation throughout the central regions of the galaxy. Too much star formation too quickly, and a galaxy burns through its gas reservoir and dies young. Too little star formation, and the galaxy becomes dim and lifeless. Sagittarius A* jets act as a thermostat, keeping star formation at a sustainable rate. It's a negative feedback loop. More gas falling toward the galactic center feeds the black hole, which becomes more active, which pushes gas away and suppresses star formation, which reduces the gas inflow which makes the black hole less active, which allows gas to accumulate again. This cycle has been operating for billions of years, and it's one of the reasons the Milky Way is a stable, long-lived galaxy capable of supporting life. If Sagittarius A* were too active, it would have blown away the gas needed to form stars like our Sun. If it were too dormant, the galaxy might have formed stars too efficiently early on and burned out. Dr. Francoise Combs from the Paris Observatory has studied the connection between galactic centers and star formation for decades. Her analysis of Webb's observations suggests that we might be living in a golden age for our galaxy, a period of relative stability where star formation is occurring at a sustainable rate, where heavy elements are abundant enough to form rocky planets, where the radiation environment allows complex chemistry to flourish. And it's all thanks to the careful balance maintained by the supermassive black hole at our galaxy's heart. But here's the uncomfortable question. How long will this balance last? Black holes spin down over time as they emit jets. Galaxies run out of gas as they form stars. Eventually, billions of years from now, the Milky Way will merge with the Andromeda galaxy. And when that happens, Sagittarius A* will merge with Andromeda's central black hole, creating an even more massive black hole. What will happen during that merger? The two black holes will orbit each other, gradually spiraling inward due to gravitational wave emission ripples in space-time itself that carry away energy. This spiral could take millions of years, during which time the two black holes and their accretion disks will gravitationally disrupt each other, potentially triggering massive bursts of star formation and equally massive jets that could sterilize huge volumes of the galaxy. And then, when the black holes finally merge, they'll emit a pulse of gravitational waves so powerful that it will shake the fabric of space-time across the entire universe. Future civilizations, if any exist, will detect this merger with their gravitational wave telescopes and study the signature to learn about the properties of the merged black hole. But let's bring this back to today, to you, sitting wherever you are right now. What does all this mean for you personally? Here's the perspective shift I want you to have. You exist in a universe where black holes aren't just cosmic monsters, they're architects. They shape galaxies, trigger star formation, regulate the chemical evolution of the cosmos, and create the conditions necessary for life to emerge. The atoms in your body are here, in the specific arrangement they're in, because billions of years ago, a supermassive black hole at the center of a young galaxy organized the chaos of the early universe into structures capable of supporting complexity. You are a pattern of atoms that arose from the interplay of gravity, nuclear fusion, chemistry, and evolution, all processes that ultimately trace back to the structure of the universe as a whole. And at the center of your galaxy, a 4 million solar mass black hole is still shaping, still organizing, still creating the conditions that allow you to exist. When you look up at the night sky toward the constellation Sagittarius, you're looking toward the center of your cosmic home. You can't see Sagittarius A* with your eyes. It's hidden behind dust clouds and too faint in visible light anyway. But it's there, 26,000 light years away, a cosmic engine that's been running for longer than multicellular life has existed on Earth. And thanks to the James Webb Space Telescope, we're finally beginning to understand what that engine really does. Now I want to dive deeper into perhaps the most profound implication of Webb's discoveries, what they mean for the search for life in the universe. And this is going to connect everything we've discussed in ways you might not expect. For decades, astrobiologists have focused on what's called the habitable zone, the region around a star where liquid water can exist on a planet's surface. This makes sense. Life as we know it requires liquid water, and you need to be the right distance from your star for water to exist in liquid form rather than freezing or boiling away. But there's a bigger picture that we often miss, a galactic habitable zone. Not all regions of a galaxy are equally suitable for life. Too close to the galactic center, and intense radiation from supernova, stellar collisions, and the black hole itself would sterilize planets regularly. Too far from the galactic center, and heavy elements needed for rocky planets and complex chemistry are scarce. Our Sun sits in what appears to be a sweet spot far enough from Sagittarius A* to avoid the radiation hazards of the inner galaxy, but close enough that we orbit in a region rich with heavy elements. But here's what Webb's observations reveal. This sweet spot isn't static. It's dynamic, and it's influenced by the activity level of the central black hole. When Sagittarius A* was more active in the past, which Webb's magnetic structure data suggests it was, its jets would have been more powerful, pushing the habitable zone outward. As the black hole has become less active over time, the habitable zone has gradually shifted inward. Our Sun entered this habitable zone at exactly the right time in the galaxy's history. Dr. Caleb Scharf from Columbia University has coined the term chronological habitability to describe this phenomenon. A galaxy isn't just spatially habitable, it's temporally habitable. There are periods in a galaxy's history when conditions are right for life, and periods when they're not. Think of it like seasons on Earth. Spring is a good time to plant crops, winter is not. Similarly, there might be seasons in galactic history where conditions are favorable for life to emerge and flourish. And we might be living in one of those favorable seasons right now. But here's where things get really interesting. If Sagittarius A* regulates the galactic environment, and if its activity level changes over time, then the emergence of life in the Milky Way might be correlated with specific phases of the black hole's evolution. What if, and this is speculation, but grounded in Webb's observations, what if life in our galaxy tends to emerge during specific epochs when the central black hole is in a particular activity state? What if we're not alone in the Milky Way, but all the other civilizations that might exist are similarly constrained to certain regions and certain time periods dictated by the black hole's influence? This would have profound implications for the Fermi paradox, the question of why we haven't detected signs of alien civilizations, despite the galaxy being billions of years old. Perhaps we haven't found anyone else because we're all living in the same relatively narrow temporal window of habitability, and any civilizations that arose earlier either died out or transcended to forms we can't detect. It's also possible that Sagittarius A* itself might be detectable as a beacon by sufficiently advanced civilizations. The jets we've discovered emit radiation across the electromagnetic spectrum. An advanced civilization anywhere in the galaxy could potentially study those jets and learn about their galactic environment. In fact, the jets might serve as a kind of galactic lighthouse, a way for civilizations to orient themselves and understand where they are in the larger cosmic structure. Now let me add another layer of mind-bending speculation. What if supermassive black holes aren't just passive architects of habitability, but active ingredients in the emergence of complexity itself? Here's the idea. Information is physical. It has to be stored in physical systems. The universe has been processing information since the Big Bang quantum fluctuations in the early universe evolved into density variations, which evolved into the large-scale structure of galaxies and clusters, which evolved into stars, planets, and eventually life. Black holes are the ultimate information processors. They take in matter and energy in disorganized forms, and, through their extreme physics, process it in ways that generate organized structures, jets, magnetic fields, accretion disks. These structures then influence the larger environment, creating conditions for more complexity to emerge. In other words, black holes might be cosmic computers, and galaxies might be the output of those computations. And if life is the ultimate form of complexity that emerges from the cosmic computation, then perhaps life itself is, in some sense, an output generated by the information processing that occurs in and around black holes. I know that sounds wild, but consider this. The universe seems to have a tendency toward increasing complexity. Despite the second law of thermodynamics, which says entropy always increases, Locally, we see complexity emerging atoms forming molecules, molecules forming cells, cells forming organisms, organisms forming ecosystems and civilizations. This emergence of complexity requires energy flows, information processing, and self-organization. Black holes provide all three. They create energy flows through their jets. They process information through their horizon dynamics. And they generate self-organized structures through their magnetic fields and accretion processes. What if the ultimate purpose, if we can use such a teleological term of black holes, isn't to destroy, but to organize? What if they're the universe's way of creating the conditions necessary for its own understanding of itself through conscious observers like us? Let me ground this philosophical speculation with some hard science by talking about gravitational waves and how they connect to everything we've been discussing. And I promise, this is going to tie together in a way that will change how you think about your place in the cosmos. In 2015, the LIGO detectors made history by directly detecting gravitational waves for the first time, ripples in space-time caused by two black holes merging about 1.3 billion light-years away. Since then, we've detected dozens more gravitational wave events, mostly from black hole mergers, with a few neutron star mergers thrown in. But here's what's coming. Future gravitational wave detectors, like the space-based LISA mission planned for launch in the 2030s, will be sensitive to much lower frequencies of gravitational waves. These low-frequency waves are generated by supermassive black hole mergers, events like the eventual merger of Sagittarius A* and Andromeda's central black hole. When two supermassive black holes merge, they emit gravitational waves for potentially millions of years before the final plunge. These waves propagate outward at the speed of light, carrying information about the masses, spins, and orbital parameters of the merging black holes. They're like sirens, announcing to the entire universe that a cosmic collision is underway. Now here's where Webb's observations become crucial. By studying Sagittarius A* in such detail today, we're establishing a baseline understanding of supermassive black hole physics that will help us interpret the gravitational wave signals we'll detect in the future. Every parameter we measure: the spin rate, the magnetic field structure, the mass distribution in the accretion disk. All of this feeds into models that predict what gravitational wave signatures to expect. But there's something even more profound. Gravitational waves don't just carry information about the black holes themselves. They also carry information about the geometry of space-time between the source and the detector. As gravitational waves travel across billions of light years, they're affected by the expansion of the universe, by the matter they pass through, by the curvature of space itself. This means that detecting gravitational waves from supermassive black hole mergers will allow us to probe the structure of the universe in unprecedented ways. We'll be able to measure the expansion rate of the universe, test alternative theories of gravity, and potentially even detect signatures of dark energy and dark matter. Think of it like sonar. When you emit a sound wave underwater, the returning echo tells you about the objects in the water and the water itself. Gravitational waves are like cosmic sonar, telling us about both the sources that emit them and the space-time ocean through which they travel. And Sagittarius A* is one of our reference points for understanding this cosmic sonar system. Every detail Webb reveals about its structure, its dynamics, its magnetic fields. All of this helps us calibrate our instruments and refine our models for when we detect the gravitational waves from the next supermassive black hole merger. But let me tell you about something even more speculative and exciting: primordial black holes. There's a hypothesis that very early in the universe, within the first second after the Big Bang, quantum fluctuations in the density of spacetime could have collapsed to form black holes directly, no star formation required. These primordial black holes could have any mass, from microscopic to billions of solar masses. If primordial supermassive black holes formed in the first moments of the universe, they would have served as seeds around which the first galaxies formed. Instead of galaxies forming first, and then somehow creating supermassive black holes in their centers. The black holes came first, and galaxies formed around them. This would solve the problem we discussed earlier about supermassive black holes existing too early in the universe. They didn't grow from smaller black holes, they were born supermassive. Now here's the truly wild part. If this is true, then Sagittarius A might be one of these primordial black holes. It might be 13.8 billion years old as the universe itself. The Milky Way galaxy didn't create Sagittarius A*. Sagittarius A* created the Milky Way. Everything we've discussed, the jets, the magnetic fields, the regulation of star formation, the creation of the habitable zone that allowed Earth to form and life to emerge, all of it traces back to a quantum fluctuation in the first fraction of a second after the Big Bang. A tiny variation in the density of spacetime, amplified by cosmic inflation, collapsing into a black hole that would eventually organize hundreds of billions of stars into the galaxy we call home. You exist because of a quantum fluctuation 13.8 billion years ago. Let that sink in. Now I want to talk about time, because black holes do something absolutely bizarre to time. And understanding this is crucial to understanding what Webb is really showing us when it looks at Sagittarius A*. According to Einstein's general relativity, time is not absolute. It flows at different rates depending on how strong the gravitational field is and how fast you're moving. This is called time dilation, and it's been experimentally verified countless times. Near a black hole, time dilation becomes extreme. If you could somehow orbit just outside the event horizon of Sagittarius A*, and then return to Earth, you would find that far more time had passed on Earth than you experienced. This isn't science fiction, it's fundamental physics, verified by every test of general relativity we've ever performed. For someone falling into a black hole, from their perspective, they cross the event horizon and hit the singularity in a finite amount of proper time, maybe a fraction of a second for a stellar mass black hole, or several hours for a supermassive black hole like Sagittarius A*. But from the perspective of someone watching from far away, they never actually cross the event horizon. They appear to slow down, get redder and dimmer, and eventually fade from view, frozen at the edge of the event horizon forever. This creates a bizarre situation. From the outside, nothing ever truly falls into a black hole. Everything that's ever approached the event horizon is, from our external perspective, still there, frozen in time. But here's the twist that quantum mechanics adds. Stephen Hawking showed in 1974 that black holes aren't completely black. They emit radiation now called Hawking radiation due to quantum effects near the event horizon. This radiation carries away energy, which means black holes slowly evaporate over time. For a black hole, the mass of Sagittarius A*, the evaporation time is absurdly long, something like 1,099 years. That's not just longer than the current age of the universe. It's longer than the age of the universe by a factor of 1,089. It's a number so large, it's essentially meaningless on human timescales. But here's the philosophical puzzle this creates. If, from an outside perspective, nothing ever crosses the event horizon, and if the black hole eventually evaporates through Hawking radiation, then what happens to all the information that fell in? Does it get preserved in the Hawking radiation? Does it somehow get encoded on the event horizon through the holographic principle we discussed earlier? Or does it genuinely disappear, violating quantum mechanics? This is the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. And Webb's observations of Sagittarius A*, particularly the strange emission lines and organized magnetic structures, might be giving us clues. If information is preserved on the event horizon, then the structures we're seeing, the magnetic fields, the emission patterns, might be manifestations of that stored information. The black hole isn't just a passive object. It's a dynamic information storage and processing system, and we're seeing its operating system in action. Think of it like this. When you save a file on your computer's hard drive, the information is encoded as magnetic patterns on the disk. Those patterns can be read, modified, and copied without destroying the information. Maybe black holes work similarly. Information falling into them, it's encoded in the quantum structure of the event horizon, and that encoding manifests as observable patterns in the surrounding matter and fields. If this is true, then Webb isn't just looking at hot gas around a black hole. It's looking at the physical manifestation of stored information about every particle, every bit of matter, every quantum state that has fallen into Sagittarius A** over the past 13.8 billion years. You're looking at the memory banks of a cosmic computer that's been running since the beginning of time. Let's talk about scale, because I think our human brains fundamentally struggle to comprehend the true scales involved with Sagittarius A* and black holes in general. And understanding these scales is crucial to appreciating both how extreme these objects are and how much. Webb's observations have revealed Sagittarius A* has a mass of about 4.15 million solar masses. One solar mass is roughly 2 kilograms. So Sagittarius A* weighs about 8.3 times 1036 kilograms. That's 8.3 followed by 36 zeros. Written out, 8,300,000,000,000,000 0 kilograms. But mass alone doesn't capture how extreme this object is. Let's talk about density. The average density of Sagittarius A* total mass divided by the volume inside the event horizon is actually surprisingly low, only about 1,000 kilograms per cubic meter. That's roughly the density of air at sea level. Wait, what? How can a black hole have the density of air? Here's the counterintuitive truth. Larger black holes are less dense on average than smaller black holes. The event horizon radius scales linearly with mass, but volume scales with the cube of radius. So as you add mass to a black hole, the volume grows faster than the mass, making the average density decrease. A stellar mass black hole might have an average density of 1 billion tons per cubic centimeter. A supermassive black hole like Sagittarius A* has an average density closer to water or air. And if you could somehow create a black hole with the mass of the entire observable universe, its average density would be less than the current average density of the universe itself, about 5 protons per cubic meter. But don't be fooled by this low average density. The singularity at the center of the black hole, if it exists as general relativity predicts, is a point of infinite density. All the mass is concentrated there, in a single geometric point with 0 volume. The event horizon is just the boundary beyond which you can't escape that infinite density. Of course, we don't really believe in infinities in physics. Whenever a theory predicts something infinite, it's usually a sign that the theory breaks down in that regime and needs to be replaced with something better. This is why physicists are so interested in quantum gravity. We need a theory that eliminates the singularity and replaces it with something physically sensible. Now let's talk about spatial scales. The event horizon of Sagittarius A* has a radius called the Schwarzschild radius of about 12 million kilometers. That's about 17 times the radius of the Sun, or about 8% of the distance from the Sun to Earth. The innermost stable circular orbit, the closest you can orbit without falling in, is about 3 times the Schwarzschild radius for a non-spinning black hole, or about 36 million kilometers. For a maximally spinning black hole, this shrinks to just above the event horizon itself. The region Webb is observing, the inner accretion disk with its jets and magnetic structures, extends from just outside the event horizon to perhaps a few 100 million kilometers out, roughly the distance from the Sun to Mars. And yet, from our perspective 26,000 light-years away, this entire region appears as a tiny dot smaller than the smallest feature we can resolve with most telescopes. It's only through the incredible resolving power of Webb's infrared camera and the Event Horizon Telescope's radio interferometry that we can see any detail at all. To put this in perspective, The angle subtended by Sagittarius A asterisks event horizon, as seen from Earth, is about 52 microsecons. That's 52 millionths of an arcsecond, or 0.00052 arcseconds. An arcsecond is 1/3600th of a degree, so we're talking about an incredibly tiny angle. To give you a sense of how small this is, if Sagittarius A asterisk were a tennis ball sitting in Los Angeles, seeing its event horizon from New York would be like resolving the individual hairs on the tennis ball's fuzzy surface. It's a testament to human ingenuity that we can observe this at all. And when Webb captures an infrared image showing the structures and variability around the black hole, it's resolving details on scales of just a few Schwarzschild radii features, only tens of millions of kilometers across, viewed from 26,000 light-years away. It's like looking at a grain of sand from 1,000 kilometers away and being able to tell its color, shape, and texture. It's absurd that we can do this, and yet we are. Now I want to bring everything full circle and talk about what Webb's observations of Sagittarius A mean for your understanding of reality itself. Because this isn't just about a black hole far away. It's about the nature of existence, consciousness, and meaning in a universe that contains such extreme objects. We live in a universe governed by physical laws that determine how matter and energy behave. These laws are mathematical at their core. Gravity follows Einstein's field equations. Quantum mechanics follows the Schrödinger equation. Electromagnetism follows Maxwell's equations. And so on. Black holes are solutions to Einstein's equations. They're not some exotic add-on to the universe. They're a natural consequence of how gravity works according to general relativity. The fact that they exist tells us that the universe operates according to deep mathematical principles that allow such extreme warping of space-time. But here's the profound part. These mathematical laws don't just allow black holes to exist, they require them to exist. Under the right conditions, when enough matter is compressed into a small enough volume, space-time must collapse into a black hole. It's not a choice. It's not random. It's inevitable, dictated by the geometry of space-time itself. And yet, from these inevitable mathematical consequences emerge complexity, structure, and ultimately, life. The same gravitational collapse that creates black holes also triggers supernova explosions that seed the cosmos with heavy elements. The same accretion processes that power black hole jets also regulate star formation in galaxies. The same extreme warping of spacetime near event horizons that creates time dilation might also be where quantum mechanics and gravity merge into a deeper theory. The universe is not random chaos. It's ordered chaos governed by laws that give rise to patterns, structures, and meaning. You are one of those patterns. Your consciousness, your experience of being you, is a pattern of information encoded in the neural connections of your brain, which is made of atoms forged in stars, which exist in a galaxy organized by a black hole, which formed from quantum fluctuations in the first moments after the Big Bang. There's an unbroken chain of causation connecting you to the very beginning of everything. And at multiple points in that chain, black holes played a crucial role. They're not separate from the story of existence. They're central characters in it. When you look at the night sky and contemplate Sagittarius A*, you're not just looking at a distant object. You're looking at part of the system that made you possible. The black hole at the center of our galaxy is, in a very real sense, part of your cosmic ancestry. And here's the final mind-bending perspective. We don't just observe the universe. We're how the universe observes itself. The atoms in your eyes, the neurons in your brain, processing this information. They're the universe examining its own structure, contemplating its own mathematics, marveling at its own extreme phenomena. Carl Sagan famously said, "We are a way for the cosmos to know itself." Webb's observations of Sagittarius A* are another example of this cosmic self-examination. We're using technology built from elements forged in stars to study the black hole that helped organize those stars into a galaxy where intelligent observers could arise. It's a strange loop. The universe creates black holes through gravity. Black holes organize the universe into structures that support complexity. Complexity eventually gives rise to consciousness, and consciousness turns around and studies black holes, completing the circle. You are part of this loop. Your existence is not incidental or meaningless. It's an integral part of the universe's ongoing process of self-organization and self-understanding. Before we finish, I want to address some of the practical implications of Webb's discoveries about Sagittarius A*. Because while the philosophical and cosmological aspects are profound, there are also very concrete ways this research matters for humanity's future. First, understanding black hole physics is crucial for future space travel. If humanity ever becomes a truly spacefaring civilization, capable of traveling beyond our solar system, we'll need to understand the gravitational environment of the galaxy we're traveling through. Black holes aren't just at galactic centers. There are stellar mass black holes scattered throughout the galaxy, relics of massive stars that exploded as supernova. Being able to detect, track, and avoid these gravitational hazards will be essential. And the techniques we're developing to study Sagittarius A* interferometry, infrared observation through dust, gravitational wave detection, are the same techniques we'll use to map the black holes throughout our local galactic neighborhood. Second, black hole physics might hold the key to revolutionary new technologies. The energy densities near black holes are the highest in the universe. If we could somehow harness even a fraction of that energy, we'd have access to power sources that dwarf anything we currently use. The Penrose process I mentioned earlier isn't just theoretical, it's physically possible. A sufficiently advanced civilization could potentially extract energy from rotating black holes. This sounds like science fiction, but it's based on rigorous physics. Freeman Dyson, one of the great physicists of the 20th century, speculated that advanced civilizations might build structures around black holes to capture this energy. Just as we speculate, they might build structures around stars, Dyson spheres. Third, the information processing potential of black holes is staggering. If the holographic principle is correct, and all the information in a three-dimensional volume can be encoded on a two-dimensional surface, then the event horizon of a black hole represents the ultimate information storage density. A black hole the size of a proton could theoretically store more information than all the computers on Earth combined. Could we somehow use this? Could a sufficiently advanced civilization encode information in the quantum structure of event horizons? Again, this sounds absurd, but we're talking about civilizations millions or billions of years more advanced than us. What seems impossible today might be routine engineering in the far future. Fourth, Webb's observations are teaching us how to search for life more effectively. By understanding how supermassive black holes regulate their galaxies, we can identify which regions of which galaxies are most likely to support life. When the next generation of telescopes comes online, telescopes capable of directly imaging exoplanets and analyzing their atmospheres for biosignatures, we'll want to prioritize targets in galactic habitable zones? The Milky Way has billions of potentially habitable planets. We can't study them all. But if we understand that certain regions and certain epochs are more favorable for life, we can focus our search more efficiently. And finally, understanding Sagittarius A* helps us understand our long-term future. The Sun will eventually die about 5 billion years from now, swelling into a red giant that will likely engulf Earth. But the galaxy will continue. If humanity survives that long, if we've spread to other star systems, we'll need to understand the galactic environment we're living in. The eventual merger with Andromeda, roughly 4 billion years from now, will be a galaxy reshaping event. Understanding how supermassive black holes behave during mergers, knowledge we're gaining from Webb's observations will be crucial for any civilization trying to survive such a cataclysm. As we come to the end of this journey, I want to leave you with a final perspective that ties together everything we've discussed. The James Webb Space Telescope looked into Sagittarius A** and found something unexpected. A black hole that challenges our models, that hints at new physics, that reveals the deep connection between cosmic destruction and cosmic creation. But more than that, Webb revealed something about the nature of scientific discovery itself. We built this telescope to answer specific questions, and like all great scientific instruments, it raised even more questions than it answered. The strange emission lines, the organized magnetic structures, the powerful mini-jets, each discovery opens new avenues of inquiry. This is how science works. We don't march steadily toward complete understanding. We stumble forward, each answer revealing new mysteries, each mystery driving us to look deeper, think harder, and build better tools. And the beautiful thing is that this process has no endpoint. There's always something more to discover, always a deeper layer of reality to probe. The universe is not just stranger than we imagine, it's stranger than we can imagine, to paraphrase the evolutionary biologist J.B. Saldan. But we keep trying. We keep building telescopes, solving equations, proposing theories, testing predictions. Because that's what conscious beings in a mathematical universe do. We try to understand the equations that govern us. Sagittarius A** represents both a physical phenomenon and a metaphysical puzzle. Physically, it's a 4 million solar mass concentration of space-time curvature at the center of our galaxy. Metaphysically, it's a challenge to our understanding, a reminder of how much we still don't know, and an invitation to keep pushing the boundaries of human knowledge. Yes, you are part of this story. Every time you learn something new about the universe, every time you let yourself feel wonder at the cosmos, you're participating in the universe's ongoing process of self-discovery. The atoms in your body were forged in the hearts of dying stars. The elements that make up your DNA were scattered across space by supernova explosions triggered by black holes. The galaxy you live in was organized by the gravitational influence of the supermassive black hole at its center. And the consciousness that allows you to understand all this emerged from billions of years of evolution on a planet that exists because the galactic environment was just right for rocky planets to form and life to flourish. You are the universe thinking about itself. You are stardust that learned to contemplate the stars. You are the cosmos examining black holes through telescopes made of matter that black holes helped create. And when you look up at the night sky toward Sagittarius, toward the galactic center, toward the invisible monster lurking at the heart of our cosmic home, remember, you're not looking at something foreign or alien. You're looking at part of the system that made you. You're looking at family. The James Webb Space Telescope showed us that Sagittarius A* isn't just a cosmic vacuum cleaner or a gravitational prison. It's a cosmic architect, a galactic gardener, a space-time artist painting with jets and magnetic fields on a canvas billions of light years across. And we're here to appreciate the artwork. Thank you for taking this journey with me. If this video expanded your mind, even a fraction as much as researching it expanded mine, then we've both grown together. That's what this channel is about: growing our understanding, pushing our perspectives, and never being satisfied with simple answers when the universe offers such profound complexity. If you enjoyed this deep dive, please hit that like button, subscribe for more mind-expanding content, and check out my video on related topic, where we explore teaser. The universe is full of mysteries, and we're going to explore every single one we can. Until next time, keep looking up, keep asking questions, and keep reminding yourself that you're a part of the greatest story ever told. Story of the universe understanding itself. And that story is far from over.